Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to continue looking at matrix operations, and we're going to look at the inverse and the transpose first. So, we've already discussed matrix multiplication, but let's look at that with the relationship to the identity matrix. The identity matrix has this unique property that if I take A and multiply it by the identity matrix, I get the original matrix back. And it works in the other order. The identity matrix times A is equal to A. Now, it is not generally true that A times B equals B times A. This is not generally true. But in this particular case, so I've got a simple little matrix here. 1 times 1, 0, 0, 1. So this is a 2 by 2. This one is 1, 2, 3, 4, 5, 6. This is a 2 by 3. These are the same, so therefore the answer will be a 2 by 3. And if I go through and look at this, in the first row, first column, I'm going to take these two combinations. So 1 times 1 plus 0 times 2, which is simply 1. And for this location, I'm going to take the second row in the first column. 0 times 1 plus 1 times 2 is just 2. And you can continue this by looking at the first row, second column, which gives me 3. The second row, second column gives me a 4. And continuing, I will term by term just end up back with the matrix I started with. So this is how the identity matrix works with matrix multiplication. Now this is important because it helps us define an inverse matrix. So I can say that B is the inverse of A if multiplying A times B gives me I, or multiplying B times A gives me I. It shouldn't matter which order I do this. And if we have this, then we're going to say that B and A are inverses, and we're going to use this notation here. Now some ways that we can write this are shown over here, where I have some rules. A matrix times its inverse is the identity matrix, or the inverse times the matrix is the identity matrix. I can also do an inverse and then take the inverse of that, and I'll go back to the original matrix. Now, to do an example, I'm going to do just a little bit of this, enough for you to see, and I'll let you finish this out on your own. But this is a 3 by 3 by a 3 by 3, which will get me an answer that it will be a 3 by 3. So these are all square, all the same size. That's going to be key. So 7 times negative 2. Remember, I'm going to take going across here with going down in the second one, plus 2 times 3, plus 1 times 9. And when I do that arithmetic, I get negative 14 plus 6 plus 9. So 15 minus 14 is 1. If I come to this next position here, 0 times negative 2, 3 times 3, negative 1 times 9, this is 0. And as you go through and do this, what you're going to find is that all the terms off the diagonal will be 0, and all the terms along the diagonal will be 1. One last little topic, and this is the transpose of a matrix. So the transpose of a matrix simply means I switch the position of the rows and the columns, essentially. So if this is 3 by 2, then the answer is going to be 2 by 3 when I do the transpose. I'm going to switch these. And instead of writing 1, 2, 3 down, I'm going to write 1, 2, 3 across, 4, 5, 6 across. One other piece of just terminology is that every once in a while you're going to run into a matrix that is square, and the transpose and its inverse are going to be equal to each other. When that happens, this matrix will be called orthogonal, and that's going to give it a lot of special properties for us when we do some of our higher order math. So this is going to complete our discussion for this. We want to describe how to take an inverse in later lessons. We want to next move on to taking determinants. Thank you very much for your time.